Hi everyone, my name is Liang. Today I'm going to present a paper named Detecting Logical Bugs of DBMS with Coverage-Based Guidance. Bugs in the DBMS, database management system, are being widely studied. Most previous works focus on detecting memory corruption bugs, which will crash the DBMS program. Existing works include generation-based Qi testing tools and mutation-based Qi fuzzing tools. However, little attention has been applied to detect logical bugs in the DBMS. Logical bugs are incorrect code logic that will make the DBMS return incorrect results. There are multiple logical bugs reported in recent years. Many of them could potentially lead to severe outcomes. There are some existing works that try to find logical bugs in the DBMS. One existing work is differential testing. The idea of differential testing is to pass the same query to different DBMS and check whether they output the same results. However, because each DBMS defines their own SQL dialects, their only limited features are shared. If differential testing only covers these shared features, we end up with low coverage for the dedicated feature for each DBMS. On the other hand, if differential testing tries to cover all the SQL dialects in all DBMS, the generated query will end up with low correctness rate. In other words, low validity. These are some sample SQL dialects from DBMS. Another existing work is SQLancer. SQLancers use Oracle to find DBMS logical bugs. And Oracle is a resource verifier that it can generate functional equivalent forms of the query for the same DBMS and check its resource inconsistencies for potential logical bugs. As a complete pipeline, SQLancer will generate its testing query using a rule-based query generator. And then it uses the Oracle to transform the query and check the results. However, for SQLancer, it relies on its rule-based query generator to generate all its testing queries. The query generation rules limit its capability to test deep program logic. In this work, we propose SQLRight, a general platform to test DBMS logical bugs. SQLRight uses coverage-guided fuzzing and validity-oriented mutations to more efficiently explore the DBMS program. And it also includes a general interface for easy Oracle development. Our tool finds 18 logical bugs in total, and we open source our tool. Here we present a motivating examples that triggers a logical bugs in the SQLite DBMS. The query creates a table, person, with column PID, and then inserts 3 rows of data, 1, 10, 10 into the table. The query then creates a unique partial index with condition PID equals to 1. And at last, the select output statements search for the table rows with constraint distinct and PID equals to 10. The correct results from this query set should be 1 row of 10 only, because the distinct keywords should remove all the duplicated results from the output. However, SQLite returns all the matching rows with 2 rows of duplicated 10s. This result is not correct. There are a few challenges we need to address in order to find logical bugs like this. The first challenge is it is hard to generate high-validity queries. To find logical bugs in DBMS, a complete pipeline of create database, insert data, output data, and check results are required. If any of these steps failed because of invalid query, the logical bug detection won't be successful. The second challenge is that it is hard to implement DBMS Oracle because first, there are no general platform existed for easy Oracle development yet, and second, it is not easy to integrate the DBMS Oracle to existing testing techniques. Take existing work SQLancer, for example. All the oracles from SQLancer are implemented by non-trivial manual efforts. So to mitigate the first challenge and to generate high-validity queries, we propose a few validity-oriented techniques in our fuzzing engine. The first technique is dedicated parsing. We noticed that most of the DBMS we tested use Python to define their parser from ends. The DBMS Python parses the input query and transforms them into DBMS unique internal structure. Thanks to the well-documented Python format, we use a translator script to transform the DBMS Python parser to SQLRight internal parser. SQLRight then uses internal parsers to transform the query inputs to SQLRight internal general IR. SQLRight mutates on this general IR in order to get a diverse set of mutated query. By using this internal parser, SQLRight can enforce the original grammar rules dedicated to each DBMS in its fuzzing mutation. The second technique is context-based IR instantiation. This technique fills in the concrete query operands based on the query context. Take this query set, for example. All the table and column names will be inserted. Notice that this step is context-based. For instance, it can correctly recognize the column name changes in the author table statements. So it can always refer to the correct column names in the select statements. There are two other techniques we use to improve validity. We leave the details in the paper. Then, to mitigate the second challenge and to fill in the missing platform for easy Oracle development, SQLRight proposed 4 general APIs: preprocess, append output, transform, and compare. The preprocess API removes improper queries from the inputs. Take this query set, for example. The random function from the insert into statements will generate a different results at different query runtimes, which could confuse the DBMS Oracle and generate false positive. In this case, the insert into statements will be removed. The second API is append output. It appends Oracle-compatible select statements to the query sets. Here, we take nowhere oracles proposed by SQLancer, for example. The select statements in the format of select something, from something, where something will be inserted. The transform API transforms the query sets to its functional equivalent forms. Take nowhere oracles, for example, again. The constraint in the where class will be moved to the select class, forming 2 select statements that are functional equivalent. And at last, the compare API allows the developers to define their own rules to verify the results. Here in this query sets, the value returned from the first select statements should match the number of ones returned from the second select. If the first select returns 1 and the second select returns 0, 1, the results are matched. However, SQLite returns value 2 in the first select statements, which are not matched from the second select. Here, the logical bugs we presented in the motivated examples is found. Here is the overview of our tool, SQLRight. SQLRight takes query from the SID inputs, mutate the query with the restriction of the per DBMS grammar rules, and then SQLRight used the DBMS Oracle to transform the query to its functional equivalent forms. After shooting all the queries to execution, SQLRight used the Oracle again to check the results and see if it can find logical bugs. And at last, if the query execution triggers a new code coverage from the DBMS, SQLRight will save the mutated query to the fuzzing queue for further exploitation. In the evaluation, we aim to answer the following 3 questions. Can SQLRight find bugs? Can SQLRight find more bugs than existing tools? And what's the benefits of our proposed techniques? We evaluate SQLRight on 3 DBMS. First, SQLRight finds 18 logical bugs in total, 14 from SQLite, 4 from MySQL. Among all the detecting bugs, 15 logical bugs have been fixed. Notice that there are 2 logical bugs are detected from newly proposed oracles. And then we compare SQLRight to 2 existing works, SQLancer and Squirrel. Squirrel is a state-of-the-art memory corruption bugs detector. We introduced the Oracle interface into Squirrel, enable it to find logical bugs similar to what SQLRight can do. From the plots, we can see that SQLRight detects the most number of bugs in 72 hours. In the same experiments, we also compare the branch coverage of the 3 tools. SQLRight detects nearly 13% more code coverage than the best baseline. And then we compare the query validity of the 3 tools. Here, SQLancer has the highest query validity thanks to its rule-based query generator. However, these rule-based generated query are not as diverse as the one mutated from SQLRight. This is proven by the lower code coverage from SQLancer in the previous code coverage plot. Due to the lack of query diversity, SQLancer does not detect as many logical bugs as SQLRight. And in the same plots, we can see SQLRight has a higher query validity compared to the fuzzing tool, Squirrel. And then we evaluate on the coverage feedbacks. We remove the coverage feedbacks from SQLRight and form 3 baselines. The baselines either drop all the mutated query, randomly save the mutated query, or save all the mutated query to the fuzzing queue. From the plots, we can see that the coverage feedbacks help SQLRight to find more bugs. And at last, we evaluate on the validity. We incrementally remove the validity-oriented techniques we introduced in SQLRight and unit test the baseline. From the plots, we can see that the validity-oriented techniques enable SQLRight to find more bugs. There are more evaluations in the paper. Please check our paper for more details. In conclusion, in this paper, we propose SQLRight as a general platform to test DBMS logical bugs. SQLRight uses coverage-guided fuzzing and validity-oriented mutations to more efficiently explore the DBMS program, and it also includes a general interface for easy Oracle development. SQLRight finds 18 logical bugs in total, and we open source our tool. Thank you for your time. I'm happy to answer any questions.